tonight's talk. Thank you so much. I guess the sound is good. I'm honored to be here and to share with you some of the research and the science that I've been thinking about and maybe a little bit obsessed about in the last few years. I have an apology first. I was told to just stay here, don't move much, but I'm Italian. 70% of my communication is nonverbal, and I walk around and I move my hands, so I'll do my best, okay? Okay, so how black holes can make nature's highest energy particles? We'll start this on a very, very basic level, just by understanding what high energy really means in astrophysics. And for that, we need to introduce high energy astrophysics. So the visible light that our eyes are sensitive to is just a very, very narrow portion of the so-called electromagnetic spectrum, the spectrum of all the possible types of light that we have in the universe. So visible right here, very narrow, and then you expand that, it goes from the blue all the way to the red. In this graph, wavelength increases to the right, frequency or energy of the photons, the individual quanta, the individual particles that are bringing this light to us, increases to the left. But you can see that there is much more in addition to the visible that our eyes are trained and sensitive to. There is a large portion on the left. These are higher energy photons. Gamma rays, the highest energy photons. X-rays that you use for an X-ray scan, ultraviolet, and then all the way to the other side, infrared, microwave, the microwave that you use, all the way to the radio band that you use in a radio. All of this is part of what we call the electromagnetic spectrum, much wider than the visible band that our eyes are sensitive to. And as astronomers, we care about all of this multi-wavelength emission that our universe can give us, and we try to understand as much as we can by combining observations that come from this whole variety of wavelengths or photon energies. So just to give you an idea of how things can vary just by looking at them with different eyes meaning visible eyes, infrared eyes, microwave eyes, X-ray eyes. These are not many sources. This is one source. Can anyone guess what this source is? The sun, right? So it's just the sun. And you can see how different it appears once you're looking at it with different eyes. The eyes that we have are giving us this picture of the sun. It's a yellowish type star, not a really very straight surface. But as you go to higher and higher photon energies, so the energies of these particles, which are to transmit the light, this is how the sun appears. This corresponds to a temperature of 2 million degrees. This, a temperature of 10 million degrees. Temperature hotter, energy of the resulting photons higher, the sun looks very different. And at these energies, you can see that it has some sort of like hair or corona around it. We actually call this extended emission outside the sun for a distance that is actually not much smaller than the solar radius, corona. We'll come back to this corona towards the end of my presentation. This is the sun, different photon evidence, different eyes looking at it. This is our galaxy. One galaxy, same object, seen at different wavelengths, photon wavelengths, different photon energies. From the radio band, lowest photon energies, all the way to the X-ray and the gamma rays. You can see how different it looks like. The visible right here, and actually the visible part for the galaxy is a little bit boring because there is a lot of dust that is preventing us from seeing the most luminous regions of our galaxy. So it's sort of like you have a screen of dust in front of you and you cannot really see the center of the galaxy where most of the stars are. But that center of the galaxy, for example, is revealed in the infrared and in the gamma ray band. If you were to look at visible light, which is what you can do with your eyes, you wouldn't see much. These various wavelengths are not all fair to us, where fair is actually ill-defined, which I will explain now. So the visible gets all the way to the surface of the Earth for good reasons. We are living here, we evolved here, our eyes adapted to the kind of light that was here. For contrast, gamma rays and X-rays are absorbed by our atmosphere before getting to the surface of the Earth. It's actually bad for astronomers because that means that they need to spend a lot of money for building telescopes that will go in outer space and observe the universe at X-rays and gamma rays, very high energies. But it's good for us because these particles, these photons, are so energetic that can cause mutations in your DNA and cancer, and we would all be dead if our atmosphere were not to be there. So we should be thankful to our atmosphere. This variety of behavior is what lets us decide whether a telescope should be built on Earth if the corresponding light of the corresponding wavelength makes it all the way to Earth, or we should launch a mission in space and so spend much more money. High energy astrophysics, out of all of this preamble, in a nutshell, is the science, the studies, how the universe looks in X-rays and gamma rays. Very often, we put the radio band in this picture too, even though the radio is the lowest energy, and high energy should be the highest energy, X-rays and gamma rays. Now, the reason for why the radio is in this picture as well, in the high energy astrophysics picture, is that very often the particles, the electrons that are emitting at the highest energies, X-rays and gamma rays, are also emitting in the radio band. Electrons are one of the fundamental particles that we have in our universe. If you are familiar with the idea of an atom, the atom is composed by a nucleus, which is usually which has a positive charge, and usually is containing one or more protons. The most abundant element in the universe, hydrogen, is just one proton. Proton is a positively charged particle, surrounded by electrons, negatively charged particles. This was high energy astrophysics. What do we do next? This is still me, so I do high energy astrophysics, but how do I do it? I'm a theorist. This is what the dictionary says the theorists should do. They should build a system of ideas that is intended to explain something. So what is that something? Is the observations. I do not do observations. The idea of the astronomer as someone that would walk to a telescope in the middle of the night, that's not what modern astronomers do. Even if they are observing, meaning collecting data, they're sitting in their office and they're telling someone else or the telescope itself how to move to collect their data. But what I do is to use that data to try to find the science, the understanding behind that data that someone else has collected. And more specifically, I do computer simulations. So I use large computers all in parallel to each other to explain the phenomena that arguably are representative or capable of explaining the data that I want to explain. And when I search simulations, I find an answer that is not very exciting. The first item that I get is the action of pretending, deception. So ideally, that's not what I do. I'm not building something that is good enough to trick you. But the second definition comes to my safety, is the production of a computer model that is able to explain something that observational or experimental data is giving us. So that's what I do, the latter, not the first. This is a little bit about me. Why this time is so exciting about high energy astrophysics. And when I say this time, I really mean the last 5 years, which on a scale of how science progresses is a very, very short time. A number of events have happened in the last 5 years, and I'm listing them here some of them here. Each one is probably worth a separate talk in itself. If any of this phenomena captures your attention and I'm not talking about it in the rest of the presentation, come and talk to me after this. So the one on the left I'm not going to talk about. These are fast radio bursts. Astronomers are not very creative. What is a fast radio burst? Is a burst in the radio band that is very fast. Okay? And that's what they are. They are as short as milliseconds, but very, very bright, very, very powerful. And we think they come from these mysterious objects that are called magnetars. Magnetars are very compact stars. They have a radius that is as big as Manhattan, about 10 miles, maybe even less. And they have super, super strong magnetic fields. The magnetic field of the Earth, in units that we as astronomers like, is 1 Gauss. The magnetic fields in magnetars is what we say 15 orders of magnitude larger than that. So it's 1 and then 15 zeros after that, Gauss. So 1 Gauss versus 1, and then you add 15 zeros, and then you put Gauss. So it's what is like a quadrillion times bigger than the magnetic field of the Earth. On the right, you're probably familiar with that image because it made it to the first page of the New York Times. That's the black hole shadow of the black hole that we have at the center of our galaxy. The mass of that black hole is 4 million times bigger than the mass of our own sun. But it's a small black hole for being at the center of our galaxy. The big ones have masses that are even 1,000 times bigger than that. So on the billion solar masses scale. But it's close by. That's why we can see it so beautifully. And for the first time, we are seeing, I mean, not really the black hole, but we're seeing all of the matter that is on the way to be feeding the black hole. And that's the matter that is shining in this ring up there. On the bottom left, the boat. So you may be familiar with GOAT. This is the greatest of all time for whatever it is, a player. So BOAT is the brightest of all time. This is a gamma ray burst. This is an explosion of a star that shines in the gamma rays. Remember, these are the highest energy photons, highest energy type of light. And they are so powerful that when they happen, they can outshine an entire galaxy. So a galaxy typically has 100 billion stars or so. And this single star, when exploding, can be brighter than those 100 billion stars. This one is an image. All of these are real images, by the way. There will be some sketches, and it will be clear that these are sketches, but these are all real images. You should always doubt an astronomer, by the way. This is a relativistic jet. These are super fast material that is emanating out of black holes. As in the introduction, the black hole is not just eating mass, but it's also ejecting matter, very often at velocities that are very, very close to the speed of light. Not larger than that. And finally, the last one we'll talk about. So I'm not going to talk about it here. So as I said, these are all events that happened within the last 5 years, and they all made it to popular press, to the news. New York Times, this was the first detection of 2 black holes merging into each other and giving out gravitational waves that were a prediction of Einstein's theory of relativity, and for the first time this has been checked and confirmed, beautifully confirmed, in 2016. Shortly after that, 2017, the 2 objects that merged were not 2 black holes, but 2 neutron stars. Neutron stars are very compact stars, same as a magnetar, size of Manhattan, but with a mass as big as the sun. Sun is much, much bigger than Manhattan, and you squeeze it into a size of Manhattan ball. That's what a neutron star is. These 2 neutron stars merged in 17. The event was called GW170817. So far, the only event of 2 neutron stars merging, but we're waiting and waiting and really waiting for the next several ones. The black hole at the center of our galaxy here, and then neutrinos down here, the gamma ray burst, the boat that I already talked about, and this is fast radio burst. But all of these events were transformational discoveries in the field of high energy astrophysics, and really let us introduce the idea not only of many wavelengths, many frequencies for the light that we receive, but also the idea of multi-messengers. So what do I mean by that? For a long time, we only had photons, light. That's how we knew about the universe. But now, we don't have just photons. We have gravitational waves from remote spaces of the universe. We have neutrinos. Neutrinos are virtually passing through the whole universe with very, very little chance of interacting. This is really fundamentally what neutrinos are. Very light particles, very weakly interacting with anything, and so they can come from very, very far away because there is nothing that is absorbing them in between. Very high energy photons. Actually, the highest energy photons have been detected recently within the last couple of years. And very high energy cosmic rays. And I will say what cosmic rays are in the next slide. But what I want to give you as an idea here is the extreme range of energies. The unit of measure of energy that is here, and it will be throughout my talk, is the electron volt. That's the energy that an electron, that single charged particle, will get if it crosses a voltage of 1 volt, which is what you have in your small batteries. So now we're talking for the neutrinos about tera electron volt. 10 to the 12 is the prefix is tera, and it means trillion. So trillions of electron volts. The highest energy photons have peta electron volt energies, what we call PeV. This corresponds to quadrillion electron volt energies. The highest energy cosmic rays, which I have not said yet what they are, have exa electron volt energies. Quintillion. I have never seen this word even. Quintillion electron volt energies. I only use EeV, okay? Exa electron volt. So just to give you a sense of scale, the LHC, the largest accelerator that we have on Earth, Jonathan was telling me before, the record holder is 13.6 tera electron volt. So it's about here, a factor of 10 larger than that. And this is a million or even almost a trillion larger energies than this. We cannot do it here. Okay? The universe is the only way we have access to such extreme energies in a single particle. I'm linking here, if the slides will be distributed, a beautiful movie that is just giving you this sense of how the universe spans a whole range of energy and length scales. From the microscopic quantities that maybe you will hear next month to the macroscopic, gigantic distances that the universe contains. Just to give you a sense of the energies then, 10 to the 12 electron volt, tera electron volt, TeV, is about the energy of a flying mosquito that bumps into your arm. Peta electron volt is the energy of this ball, if I'm dropping it. And exa electron volt is the energy of this tennis ball. If I'm throwing, I'm not throwing it. If I'm throwing it at you with a speed of 100 kilometers per hour, which is what professional tennis players would do. In a single particle. In a single particle. So the energy of this ball in a single particle. This multi-messenger picture can give us much more information than just photons. This is a plot illustrating that. The energy, oh, it's cut. Actually. Oh no, it's right there. The energy is here on the horizontal axis. This is the distance up to which you can see a photon or a neutrino or a cosmic ray, which admittedly I've not said what it is, from those distances to us. So all of this black region, you cannot get photons from. The photons interact with light from stars. Such high energy photons interact with light from stars, and they annihilate. They produce an electron and a positron, which is the friend of the electron with the opposite charge. Neutrinos, on the other hand, can come from everywhere in the universe. So if you have a source of neutrinos somewhere, as I said, the neutrinos are so weakly interacting, so unfriendly with anyone else, that they come all the way to us. New messengers are giving us alternative views of our universe. Now I'm finally ready to tell you what these cosmic rays are. So they were discovered in 1912 by Victor S., an Austrian physicist, that performed a balloon experiment. He went onto a balloon with an electroscope. The electroscope would just measure how much charges are hitting it. And he flew up to 5 kilometers approximately. So what he found was that as he was getting higher and higher, initially the electroscope was dropping its counts. That's consistent with the fact that most of the charged particles come from actually the Earth. The Earth contains some radioactive material. The radioactive material produces charged particles, and that's what he was measuring. But then as he got higher and higher, the trend reversed. And instead of dropping the number of counts increased back up again. So that meant that the source could not be the Earth at such high altitudes, but it could be, and it should be, extraterrestrial. Extraterrestrial in the sense of outside of the Earth, okay? Don't think about like little green men. So these are now solidly accepted to be charged particles, protons, other nuclei of atoms, electrons of extraterrestrial origin. This is what cosmic rays are. Neutrinos don't have a charge. Photons don't have a charge. The only charged particles that I will talk about as messengers are cosmic rays, and primarily protons. The next slide is more like on a fun aspect. There was an extra, the next experiment that probed the physics of cosmic rays was performed by Picard. He reached the stratosphere in a gondola attached to a balloon and measured cosmic rays, settling this question that they are indeed particles of, charged particles of extraterrestrial origin. Now, if you're a Star Trek fan, you would realize that Jean-Luc Picard, yes, was named after Picard. Second aspect, this gondola was used not just to go all the way up in the stratosphere, but also all the way down. Picard and his son, Jacques, dove to 3,000 meters deep in 1954, and I think after that they even reached lower depths or higher depths. Two fun facts. Okay, so how do we quantify these cosmic rays? This is maybe the most important plot when talking about cosmic ray research. You're essentially measuring as a function of their energy, again, this unit of electron volt, tera electron volt, peta electron volt, exa electron volt. This is zeta electron volt. We didn't even talk about that. That's a 6 and here is how many we get. So the flux is a statement about how many you are receiving per unit area. So let's say in between my hands per second. In this plot, and you'll see other realizations of similar plots, both the vertical axis and the horizontal axis are in logarithmic scale. And the fact that this is a straight line corresponds to a functional form of the energy of the cosmic rays, that energy to the minus 2.7 power. This is called power law. It's one of the fundamental laws of very high energy astrophysical sources. It's often in a power law distributed fashion. Essentially a power law in this logarithm plot, it's a straight line. But it's not a perfectly straight line. And in fact, we like to humanize things. We call this knee and we call this ankle, right? It does look like a human leg. There are lots of questions on this spectrum. Where are these particles originating from? What I will really be focusing will be the highest energy of those. And how do we detect those highest energies? Thankfully, the atmosphere is still protecting us. So these super high energy charged particles don't make it to the surface of the Earth. They produce this so-called shower. So they interact with the atmosphere, and their energy is partitioned into a number of secondary particles that come from the interaction of the primary particles with atoms in our atmosphere, thus creating this shower. And that's exactly how we detect them. This is one of the experiments that is used. It's called Pierre-Auger experiment. It's in Argentina. And it's super big. The reason for that is in this plot again. I should emphasize that at the knee, you're getting about 1 particle per square meter, square yard per year. At the ankle, you get 1 particle per square kilometer per year. So you need your detector, you need your experiment to be a square kilometer in order to detect 1 particle per year. So how do you solve that? Your detector is very big. So the one in Argentina, Auger, is distributed over a surface of 3,000 square kilometers. And this surface is filled with water tanks. The cosmic ray primary particle is creating this shower of secondary particles. The secondary particles, once they move through water, they are moving so fast that they're faster than the speed of light in water. In water, the speed of light is a little bit lower than in vacuum, and these particles are faster than the speed of light in water. So when that happens, they emit light. This light is called Cherenkov light. That's what you can see here. That's why these detectors are called Cherenkov detectors. I'm spending time on that because the same detection technique is used for neutrinos. That would be the very last point of my presentation. But they're big. They need to be big, just because these events, these very high energy particles, are so rare. And this one was an exceptional event. In 1991, an experiment in Utah detected a particle with energy of 300 exa-electron volt. So exa-electron volt was the largest one that I had in my 3-panel plots. So 300 times larger than the kinetic energy of a tennis ball thrown at 100 kilometers per hour. And in fact, this particle was called the oh my god particle because we were not really expecting to detect energies so large. I can give you an estimate of its energy in other ways. This particle is traveling so close to the speed of light that if it were to travel the whole universe, a photon, which is moving exactly at the speed of light, would be leading this particle just by a few miles throughout the whole length of the universe. Or the kinetic energy is the kinetic energy of a baseball that is much heavier than a tennis ball thrown by a professional player. And in fact, we were not really expecting these particles because there is a limit that is called the GZK limit, such that high energy charged particles coming from very far away cannot really travel very large distances. They interact with the leftover of the Big Bang. That's called cosmic microwave background radiation. It's essentially the leftover of the hot state in which our universe was very close to its birth. So where do they come from, right? Where is the origin of cosmic rays? This was a review that was written in 1957, and I just want to emphasize that the topic of cosmic rays was appreciated by Einstein as well. He said, arguably, that two phenomena show a deep lack of our knowledge of the physical world: cosmic rays and the magnetic field of the Earth. So I actually cannot say much about the field of the Earth. It's not my field. But I can say that we have gotten to know a little bit more about what the origin of cosmic rays can be. Fermi, famous Italian physicist, was very instrumental for that. He proposed a theory for the origin of these cosmic rays in 1949. And that theory essentially said that these cosmic rays are energized, they're accelerated, they're energized by bouncing off magnetized clouds in our universe. I'll make that statement a little bit clearer later on. The idea is exactly like this. So I need Asia's help now. The mechanism that is often invoked for energizing these particles is called the Fermi mechanism. The basic idea is that you essentially have two tennis players that are moving either toward, start further away and then move close, that are moving either towards each other or away from each other. So I'll throw the ball at the board. What you will see is that as she approaches, the ball will come back with a larger velocity, okay? Because she's moving towards me. Let's do it. A little bit more. Yeah, come. And now we'll do the opposite experiment. Oops, I'm not very good, clearly. In which she is receding away from me at the same speed. And you see the ball came back with a lower velocity. Now, we just practiced 5 minutes before this presentation, so I'm sure we can do better next time. But that's the idea. Thank you, Asia. So the basic idea is that if you have something moving towards you and you have an elastic collision, then you get an energy gain. If something moves away from you, then you lose your energy. You get energy loss. There is a particular configuration in astrophysics where this process is very efficient and you only have collisions that are allowing you to increase your energy, and that's a case of a shock. The shock is a discontinuity in pressure that you have whenever you have very fast flows. If you have your plane and the plane is moving faster than the speed of sound, ahead of the plane will form a shock. If you have heard statements like, oh, this plane is moving at a Mach number of 1.5, the Mach number is just the ratio of the plane velocity to the sound speed. And when that number is larger than 1, you have to form a shock. So shocks are great for the mechanism that Asia demonstrated for energizing particles. But I talked about collisions. And in astrophysics, in most of the universe, the particles don't really collide with each other. The densities are very, very, very low. So how do you collide? What do you collide with? And that's where Fermi's intuition really made the difference. He said essentially that the particles don't collide with each other, but they effectively collide with magnetic fields. So you can see the movie at the bottom. You'll have one particle in a magnetic field. The particle will gyrate around the magnetic field, effectively coming back. Same thing as a collision would do. The particle doesn't move anymore in a straight line, but the magnetic field is bending the particle back. That's what magnetic fields do. They're very good at bending particles. So that particle comes back, and then it starts gyrating more and more. But the effective collisions that are responsible for energization, for the simplest model of energization of these high energy particles, relies on collisions with magnetic fields. Now, I told you this story, and it's been a story for some time, yet it's not a complete story. And particularly the challenge is for the highest energy particles. The highest energy particles with energies in excess of exaelectron volt or hundreds of exaelectron volt, or like as the oh my god particle 300 exaelectron volt, are very hard to explain for any astrophysical source. This plot is explaining that. It's showing various astrophysical sources. We talked about some of them. These are gamma ray bursts. These are the super bright explosions that can outshine a galaxy. These are jets, relativistic ejections of materials from black holes. Magnetic field in these sources, size. What this plot shows is that in order to be able to accelerate a particle, the particle needs to be staying in that accelerator. And more precisely, the radius, the distance over which it gyrates around the magnetic field, as we said, magnetic fields are very good at letting particles gyrate around, needs to be smaller than the size of the source. Otherwise, the particle will have left. This plot is called Hill's plot, and it's just saying how hard it is to produce a proton of energies of 100 exa electron volt, 10 to the 20 electron volt. Very few astrophysical sources are even barely touching that limit. And no source can say, oh, I can confidently do it. So the challenge is uniquely difficult for the highest energy particles in our universe, the ultra high energy cosmic rays. Energy is close to the oh my god particle. So the Fermi picture is correct, but it's not enough. So I want to show you a realization of that process that Asia helped me to visualize. This is one of our simulations. I will say later how we run these simulations, what technique we used. This is the shock. This is that discontinuity that you have when you have a very fast supersonic flow, a flow that moves faster than the speed of sound. And you should imagine these rockets to the right and to the left of the shock to be your boards, the boards that she used, the boards that are allowing the particles to be reflected back and back every time with a higher energy. So what we see in the simulation is that the particle indeed gains energy by this process. This was hypothesized, not seen, and for the first time in 2010 or so was seen directly in the simulation results, in the computer simulation results. So the particle is right here, and you will see the trajectory of this particle going back and forth across this surface at 0. At the same time, the energy of the particle in the bottom panel will increase. So I'll just let you appreciate it. The trajectory is made a little bit longer, but what you should gather for this is that indeed you see this motion back and forth. When it goes back, it will be very clear at this stage you will get a kick in energy, which is exactly what the prediction of the Fermi process describes. So what happens now, it will go back and get a kick in energy. So the Fermi process is real, but it's not enough. And why it's not enough? Because for these conditions it's too slow. In order to be able to produce very high energy particles, you also need to be doing it fast. The sources have a limited lifetime. If you have an explosion of a star, you have a certain time for the explosion. You have a certain time that you have available to accelerate that particle. So the challenge is to find not just an accelerator, but an accelerator that can accelerate fast. And that's the rest of my presentation. So the difficulty is to find that. And very often in astrophysics, we have this limitation of not being able to reproduce experiments. Okay, you have an explosion, that's it. So very often the work that we do is by inferring conditions from the outcomes. You detect some particles or you detect some photons, and then you're trying to infer what happened without the possibility of replicating it or, oh, let's have it happen again. Doesn't work that way. And very often you can be manifestly wrong. So these are the exhausts, and you would not think this to be the engine. Okay, so we have limited power in our inference. So what I do in my research is the other way around. I try to focus on the engine, and then I try to produce the exhausts. What comes out of that? What kind of particles I can make? And then the question is it enough to explain what the observations are telling us? So the new mechanism that I'm going to propose or talk about is called magnetic reconnection. And it's a process that was discussed in these terms by Russell Kasrud at Princeton, one of the pioneers of this field, at his 90th birthday party. Enrico Fermi, still Fermi, told me to study reconnection for my PhD thesis 70 years ago, and here we are, and we still don't understand it. Now, we have made some steps in the direction of understanding it better. I wouldn't say that we understand it fully, but we understand it better. So what really understands reconnection is Wikipedia. This is a Wikipedia picture of what magnetic reconnection looks like. So the magnetic field can be described by these arrows, blue and red. And as you can see, the blue points to the right, and their end points to the left. When they meet in the middle, they don't really like to preserve their identity, and they end up being ejected to the left and to the right, half blue and half red. So in more technical words, magnetic reconnection is a way to rearrange the geometry of the magnetic field. And once you do it, at the same time, some of the energy of the magnetic field can be released as particle energy and potentially accelerate some particles to very high energies. And if you're asking whether this happens, yes, this happens. And the rest of my presentation will be focused on what reconnection can do in the perspective of high energy particles in the universe. Reconnection is not a peculiarity of remote astrophysical systems. It does happen near us. This is a manifestation of reconnection in the sun. This is an actual movie of the vicinity of the solar surface, and this is the effect on larger distances. Now, the movie will hopefully loop back. I want to emphasize this ejection, this eruption. This is triggered by the release of magnetic energy through magnetic reconnection. It happens near the Earth due to the effect of the solar wind, the wind coming from the sun, impacting the Earth. It snaps on this side, it's called day side because it's facing the sun, and it snaps on the other side called night side because it's opposite to the sun. This is an artist's depiction. But it happens everywhere. It happens near the Earth, it happens near the sun. There is a peculiarity of astrophysical systems that when it happens, it can release a large portion of magnetic energy. So the parameter that we often use is this one. Essentially, you should think about it as how much magnetic energy you have as compared to how much particle mass you have. And for astrophysical scenarios, this parameter can be much larger than 1. So reconnection, when it happens in this regime, is called relativistic. Why? Because it can accelerate particles to extremely relativistic energies. And it does that very fast. The velocity that is most important for reconnection is the velocity at which the gas, the plasma, the fluid flows into this region where the magic happens and where the magnetic energy is released to the particle. So for the conditions that we expect for astrophysical sources, this velocity can be as large as 10% of the speed of light. 10% of the speed of light. So that's the rate, that's the speed at which you are able to convert the energy of your magnetic field into energy that can be used for particle acceleration. So it looks like a promising candidate. Oh, if you want to bore yourself with 40 pages of technical stuff on reconnection, I wrote recently a review. If you're interested, okay? This is meant to be not for general audiences, but also not super specialistic, so you might enjoy. So how do we do it? As I said, I'm a numericist. I work with computer simulations. The method that we use is called particle in cell, because you have particles in a computational cell. We solve fundamental equations of electromagnetism. The equations invented and discovered by Maxwell are telling us the electric and the magnetic fields. The equation discovered by Lorenzo, not me, Lorenzo, are using the electric and the magnetic fields to push the particles, the charged particles around. That's basically what we do. We push particles around with electric and magnetic fields. As I gave you a description earlier, the magnetic field is very good at bending a particle. The electric field is very good at accelerating a particle. So that's a very good candidate for giving us what we want. And then you keep doing it. For trillion particles, as of today, quadrillion particles are within our computer capabilities. So I did this calculation before this presentation, and I realized that in my career, about 10 years since I got at Columbia, I spent 50,000 CPU years. So a CPU is basically a computer unit. So effectively I used 50,000 years of a single computer. I didn't really do that. I used many computers, but effectively the amount of resources that I used is over 50,000 CPU years. So how does reconnection look like? This is reconnection in the regime that we are expecting it to be relevant for the acceleration of high energy cosmic rays. As I said, the basic setup is a setup in which the field is flipping. These are the equivalent of the blue and red lines of the Wikipedia movie. And now this is a simulation, one of the state-of-the-art simulations of reconnection in 3 dimensions. We are pinching it in the middle, and then it evolves by having these 2 fronts moving left and right. What you should see here, this is density, so how much mass you have, how much density you have, that it's very structured. We call these structures magnetic islands or flux ropes or plasmoids, but the main point is that you have a variety of structures. Now we'll use them later. Now one thing, sorry, let me go back. One thing that I have not justified yet, so we want to put these pieces together. I haven't said anything about black holes yet. So I've said something about reconnection, but reconnection now I want to justify happens in the vicinity of a black hole. So this is a simulation of accretion onto a black hole. Accretion is the process by which the black holes are acquiring mass. And this is indeed the rate at which the mass is being eaten. The mass of the surroundings is feeding the black hole, or the mass is being eaten by the black hole. And the accretion rate, or I would say the eating rate, is very bursty. So you have these very short episodes of significant food intake, separated by these very long episodes in which not much, the curve is lower, meaning that not much mass is being eaten by the black hole. So the black hole is eating a lot and then resting for a while. And this is associated with a very characteristic morphology very near the black hole. So this is what the 2 panels here are suggesting. Pick your favorite one, it doesn't matter, they're showing different quantities. The one on the left is the density. So what you will see here is that there are episodes in which the black hole is spitting out this density. These are the episodes in which the black hole is not eating much. And before those events, you see these little blobs. They are admittedly very small, but these little blobs are the same blobs that I showed earlier in the reconnection simulation. So this is evidence that that process of killing the magnetic field energy and potentially releasing it to the particles is happening in the close vicinity of black holes. And this is true for black holes that have small mass, black holes that have very large mass in the centers of galaxies. So reconnection is happening in the vicinity of black holes, in what we call the black hole magnetosphere, the immediate magnetized environment of the black hole. So what do we do with this? We produce high energy photons and we produce neutrinos. So let's get to the photons part and then we'll conclude with the neutrino part. Now I'm listing the people that have collaborated with me on various projects. Probably their name doesn't mean much to you, but I want to acknowledge them because they are the ones that have done most of the work. Especially more junior people are really the ones that are driving the science. So the photon application that I have in mind refers to a system that is called X-ray binary. This is the system, this is an artist's depiction. This is a system, I wish we could have images like that. This is a system of a black hole. The black hole is sitting here that is accreting mass, it's getting mass from a companion star. These 2 objects are moving around each other. The star is giving its mass, part of its mass, to the black hole. And the black hole is eating it. These systems exist in 2 states. One is called soft, the other one is called hard. So soft state means that the photons that we're getting are a little lower energy. The hard state means that the photons we're getting have higher energy. And these systems in the plane of X-ray hardness, so soft will be here on the left, hard will be here on the right, and luminosity, so how bright they are, they form this very characteristic Q diagram. They keep going around. You see, over time, they just populate this more and more. Very interesting, unexplained. Ask me about that, but I don't have good answers. What I would like to give you is how a reconnection can make the hard state. In the hard state, as I said, most of the photons, this is photon energy, is high. This is 100 keV. 100 keV is in the X-rays, but very high energy X-rays. The soft state is usually very easily explained by the picture that I had in the previous slide. This is emission, standard emission expected from this disk of material that moves around the black hole before eating the black hole, before feeding the black hole. The hard state, unknown. Higher energy photons, where do they come from? The usual picture is attributing these high energy photons to an emission, to a region that is called corona. Now we have a corona, as I said earlier, in the case of our sun. This is the region just above the solar surface that can reach temperatures that are much, much larger, millions of degrees larger than the solar surface itself. And we think that even in the case of our sun, this process of magnetic reconnection is responsible for giving the hot temperature of the corona. So can reconnection work in a corona of a black hole? We don't really know what the corona would be for a black hole. We don't have a characterization of its properties, but we can proceed by analogy with the case of the solar corona. So the process that works for making those high energy photons is called Comptonization. Comptonization is depicted here. You have an electron, you have a soft photon. The soft photon, low energy photon, is being kicked up in energy by the electron. This is the same process that Asia and I described earlier. Previously, you had a charged particles that was hitting a wall or a board, and it was getting higher in energy. Now you have a photon that is hitting an electron. The electron has a lot of energy, and the photon will receive some of that energy and be promoted to even higher energies. Same physics. This is effectively the Fermi process, but for photons. Where? Corona, we have no idea what the corona of a black hole is. I have some ideas, but those are still ideas. The question, though, is what is the process that can be giving these kicks to the photons to higher energies? So I'm going to skip this. And you might suspect now that the process that I'm invoking is magnetic reconnection. So why and how magnetic reconnection will do that? You should imagine here photons roaming around the whole box. Reconnection is producing those plasmoids, magnetic islands that are moving. So effectively, these magnetic islands can be the electron in the previous plot that can kick up, that they can kick the photon up to higher energy. And in fact, that's what we're finding. The photons are being energized by the motions of these structures that we call plasmoids or magnetic islands that reconnection naturally produces. We can produce models, we can produce spectra of distributions of photons that come out of our simulations. These are the dotted and the dashed lines here, and the actual observational data are the orange and the blue data points. So you can see that the dashed line is just perfectly on top of the orange and blue data points. So reconnection, I would say we have now, I think the community has been convinced as well, I hope I've convinced you as well, that reconnection near a black hole in the corona, even though we don't really have a very good idea of what the corona is or what it is, may be responsible for these very hard photons, very high energy X-ray photons that we see in the case of a black hole eating matter from a companion star. And in the last 5 minutes, I'll talk about high energy protons and neutrinos. So I sold you the story of reconnection as a very good particle accelerator. This is an example of a particle that is accelerated in reconnection. The particle will be here, and this movie will proceed. It's a three-dimensional simulation. In this plane, the magnetic field is like this. In the other plane, you're rotating it, so the magnetic field lines come towards you and away from you. But it's the same simulation and the same particle in this simulation. So you can see the particle is stuck for a while in the structure, in these magnetic islands, but then it breaks free and it starts doing this oscillatory motion up and down. We call it like freestyle swimming because it's sort of like reminiscent of freestyle swimming. The advantage from the point of view of this particle is that it can be energized very, very fast. As fast as you need to make ultra-energy cosmic rays. This is a statement about the energy of the particle versus time, and this dashed line is sort of like the highest you can ever expect to accelerate a particle in our universe. And you can see that this particle is accelerating at a rate that is very close to that red dashed line. So the conclusion that we got is that reconnection is able to make ultra high energy cosmic rays. The best environment for that is the case of AGN jets, of relativistic jets from supermassive black holes. Now I will conclude with the beautiful IceCube experiment. This is an experiment that is situated at the South Pole in the Amundsen-Scott South Pole Station. The detector is the ice of Antarctica. You have neutrinos coming through, producing secondary particles once again. The secondary particles are moving faster than the speed of light in ice, and they produce light. And that's how we can detect them, and we can infer that a neutrino caused them. The highest energy neutrino detected today is of order an exa-electron volt, but the most interesting neutrinos are coming from a source. So now we can say, oh, the neutrinos are coming from that object, and that object is an accreting black hole. The galaxy is called NGC 1068. Name is not very important, but we have now detected more than 100 neutrinos. This number was a little outdated. The initial detection was 79 neutrinos, and now we have much more than that. So it's clearly the first object that has been seen in the universe as a source not of photons, but of neutrinos. And we can directly point at it because the neutrinos don't bend in the magnetic field. They are not charged, so they don't bend. And the most compelling explanation of these neutrinos is that they come from the same region where the very high energy X-ray photons that I just talked about of coronal origin are coming from. I'm a little out of times, and these are probably more technical than I would like to, but let me just end with a couple of remarks on the neutrino new window that IceCube has opened. The sources that we have seen so far seem to be associated with very highly accreting black holes that are eating a large amount of mass per unit time. These black holes are also seen in the X-rays as very bright X-ray sources at high X-ray energies. This is X-ray band right here. And yet, not much is seen at higher photon energies. This is the neutrino signal. This is the photon signal at the same energies. This was a big puzzle because all of our models are saying that if you have a proton that makes a neutrino, it will also make a gamma ray, high energy photon. And yet, we see the neutrinos, but we don't see the gamma rays. So the explanation that we have now, and that's supported by the model that we have worked on, is that the source, this corona region around this very highly accreting black hole, is so small that the photons cannot get out. They are degraded to lower energies before getting out. The neutrinos, on the other hand, as I told you, they're very resistant to talking to anyone. So they can stream freely out of this very compact, very dense region and get all the way to us. So the photons would be there, but they're absorbed locally, and that's why we don't see them. And these are the details of our models, and we have built a quantitative picture that matches the data. This butterfly diagram is what the data was from IceCube, and the red line is our model. And we also show that the photons are not as are absorbed. So all of this data are saying that the photon flux should be lower than this. And in fact, our model says that the photon flux indeed is not very high because all of the photons are trapped in this very compact, extreme region around the black hole. So with that, I will conclude. This is my summary. You'll see maybe the 3 most relevant pictures that I gave you here, other than the demonstration we did with Asia. That is probably the main thing you will remember. Anyway, thank you so much, and thank you for the attention.
Okay.
And, you know, I was expecting to talk for 30 minutes. I mean, based on what I prepared. But I enjoyed it so much, so thank you for being here that I ended up talking for 1 hour.
Yes.